Welcome back, everyone, to another edition of The Explainer. Today, we're diving straight into the absolute lifeblood of an incredible aircraft. We're talking about the Bombardier Q400 Engine Oil System, specifically ATA-79. I'm super excited to guide you through this, so let's jump right in.
Real quick, here's our flight plan for today's briefing. We're going to methodically break down 6 key areas. We'll start off with core lubrication and capacity, then move right into temperature and pressure controls. After that, we'll check out the remote oil indication option and its display conditions. And finally, we'll wrap the whole thing up by decoding the oil temperature and oil pressure display callouts you'd see right there in the cockpit.
All right, Section 1. Let's look at the physical tank itself and our core lubrication targets.
So to set our physical baseline, we need to know exactly what we're working with, capacity-wise. This system's main job is lubricating 3 crucial components: the bearings, the gearboxes, and the propeller. To do that, it uses an integral tank with a total capacity of roughly 6 US gallons. And yes, it comes with the traditional sight gauge for manual quantity checks. A really handy way to lock this into your brain is BGP6. Bearings, gearboxes, propeller. 6 gallons.
Now here's the catch. You absolutely have to know when to check that sight gauge. There's a very strict 15 to 30-minute window right after engine shutdown. If you check it too early or if you wait too long, your reading is just not going to be accurate. A simple trick? Just think quarter to half. That's your 15 to 30-minute post-shutdown window. Moving on to Section 2, let's see how the physical systems actually manage extreme heat and pressure.
When you're up in the air, the oil temperature doesn't just manage itself. It's actively controlled by the air-cooled oil cooler, or ACOC for short. This little powerhouse has an internal thermal bypass valve and a flap door. Now that flap door is controlled by an electrical actuator that responds directly to the oil's temperature, opening and closing to precisely manage the airflow through the cooler. An easy memory hook for this one is ACT. Actuator controls temperature via the flap door. Now what about pressure? Well, there's a very specific pressure drop that will immediately trigger an overhead warning light in the cockpit. If the oil pressure drops below 47 plus or minus 3 psid, a low oil pressure switch gets tripped, and bam, the respective engine's warning light comes on. To remember this threshold, just tell yourself, under 47, look to heaven, because you're going to be looking up at that overhead warning light.
All right, Section 3. Let's talk about the optional remote system. This is a huge time saver for ground crews and pilots, so they aren't just relying on that physical sight gauge.
Located right there on the pilot's forward side console, you might find the optional remote oil level indication system. It's incredibly useful because it gives the crew a heads up when the oil drops to 10 flying hours or less, based on nominal consumption rates. The coolest part? It works even when the engines are completely shut down. But it'll only give you a reading when you explicitly flip the system interrogation switch to the on position. A good rhyme for this? 10 hours to go, flip switch to no.
On to Section 4. Let's unpack what the visual feedback from those 2 green indicator lights actually means when you're using the system. There's a really strict no-nonsense correspondence between what the system senses and what the pilot sees on the panel. If you see a steady green light, you're good. Oil level is okay. A flashing green light, that means the level is low. But what if there's no light at all? Well, that means you don't have a valid reading, which mandates a physical checkout at the engine per the manual within 10 flying hours. To keep it all straight, just remember, steady is ready, flashing is low, none means go, as in go do a physical check.
The way this digital relay works is pretty fascinating. The standard old-school dipstick is effectively replaced by a highly accurate sensor assembly. This sensor generates a discrete signal that travels directly to the FADEC. From there, the FADEC routes that information straight to the EMU, which handles all the required logic, verification, and monitoring. The transmission path is a straightforward SFE, sensor to FADEC to EMU. Okay, Section 5. Let's shift our focus over to the digital engine display in the cockpit, starting specifically with how we read oil temperature. So when you look at the digital engine display, the oil temperature readout actually covers a massive operating range, from -99 all the way up to 199 degrees Celsius. This gets visualized by an analog needle that sweeps across 7 distinctly colored arcs: white, red, yellow, green, yellow again, red again, and finally white at the top end. Now, if that parameter ever becomes invalid for some reason, the digital numbers instantly vanish, replaced by white dashes, and the entire dial reverts to just a simple white arc. To memorize this layout, just picture the 7 arcs of heat. Now for Section 6, let's compare that temperature dial to the totally different scale behavior we use for monitoring oil pressure. Unlike the temperature gauge, the oil pressure needle has this really dynamic layout that actively expands during normal operation. It shows a digital value ranging from 0 to 299 psi, with an analog needle moving across 5 colored arcs. What makes it totally unique is that it utilizes 3 different scale factors to purposefully expand the normal operating range right between the 2 and 3 o'clock positions. Plus, the scale won't even appear on the screen until pressure is actually sensed during the engine start sequence. A quick way to recall this is 35299. That's 3 scale factors, 5 arcs, indicating up to 299 psi. So the absolutely crucial takeaway here is observing the subtle but super essential differences in how the Q400 continuously monitors temperature versus how it distinctly activates for pressure. The temperature scale, it's always there, always presenting its 7 colored arcs. The pressure scale, on the other hand, waits patiently until engine start to dynamically reveal its 5 arcs, utilizing those 3 distinct scale factors.
And that brings us to the end of our deep dive today. When you really think about it, with 3 scale factors intelligently expanding the normal pressure range and discrete sensors routing data directly through the FADEC right to the EMU, how much more intuitive will future automated engine monitoring become? It is honestly incredible to see the level of precision already built into the Q400 ATA79 system today, and it definitely leaves us wondering what the next exciting evolution of aviation displays is going to look like. Thanks so much for joining me on The Explainer, and as always, keep learning.